Okay, dear students, in this video we are going to see stability of keto form and enol forms. What are the factors which affect the stability of enols and keto form? Okay. Now let's proceed in step by step. See, if you look at acetaldehyde with different examples, let's see. Acetaldehyde, what is its enolic form? CH2 double bond CHOH. Okay. Vinyl alcohol, this is vinyl alcohol, this is acetaldehyde. Here, this, see, acetaldehyde is more stable than 2 enolic form because C double bond O becomes as C double bond C, but its bond energy is more than this. So naturally this is more stable, less energetic and more stable. Okay, that's why bond energy means that is the released energy, right? Next, similarly, if we take acetone, here also, see what you get, CH3, C double bond O, sorry, COH, C double bond CH2, enolic form, keto form and enolic form. Here also, one is more stable than 2. More stable than 2 for the similar reason. Now, let's take diketo compounds. Diketo compounds. See, the two, first let's take this compound. See, this is keto alpha beta. Beta, this is beta diketones. Alpha beta, see, this is say beta diketones. Next, if you look at this one, say this hydrogen, we already seen in first video, these hydrogens participate in tautomerism with either structurally both the ketones are same. So you can write like this, OH double bond, here double bond O. This is keto form, this is enol form. Here enol form is more stable. Enol form is 2 is more stable than 1. Why? 2 is more stable than 1. Why? Because 2, in 2, see, there is a conjugation, double bond, single bond, double bond. So resonance stability. See, reason, one is resonance stability. Another one is intramolecular hydrogen bond. See, these two factors are responsible for the stability of enol. It is about 76% when compared to this. In this mixture, it exists as 76%. Okay, this is more stable. Now let's see comparatively, if, see this, if it is an ester, COOET, if it is an ester, we already seen this double bond O participate in first video, we have seen this double bond O participates in tautomerism. Again, these hydrogens, see this, because, see, once let's see the reason again, because the C double bond is in conjugation with this lone pair on this oxygen atom. So it has two options. It can be with, it can show or may not show withdrawing effect on this, but this always shows. So its withdrawing effect is more on this. This is OH, here double bond, here double bond O, AT. Here also same. But if you compare, say let it be 3 and 4, 3 and 4, but its enol form is less. Enol percentage is about 7% or something if you look at the experimental values. Why? See what I told you, this enol system is stabilized by resonance. Here also resonance is there. But this C double bond O is in crossed conjugation. It may be in conjugation with this or with this lone pair. Means resonance stabilization of enol part by this decreases when compared to that. That's why percentage of enol decreases. Suppose if this group is also replaced by an ester, if it is also replaced by an ester, see what happens. Further percentage of enol decreases the same way. Further percentage of enol decreases, it is almost nil. Here percentage of enol is almost 10 power minus 3%, negligible. Because of, see, for similar reason, because of cross reconjugation, stabilization of this is less, and also enolization of this a little bit when compared to this less. These are the different factors. So among these, its percentage is highest. Next to this one, next to this one. Now let's change the problem. If you take fourth problem, if a phenyl system is introduced, sorry, this third problem, 4, 5, sixth problem. If a phenyl system is introduced, phenyl, C double bond O, see keto group. See, let's draw the enols with this because it is in conjugation with this. Okay. Here percentage of enol, see when compared to 2, its percentage of enol is more because of extended conjugation. See here aromatic system is there. Resonance stability of molecule, total resonance stability of this molecule is more when compared to this. That's why when compared to this enol, its percentage is more. If another aromatic system is introduced, see, its enolic form, it is almost 100%, almost 100% because of extent of resonance. Total resonance stability of molecule is more. Okay, that's why. So these are the different examples, comparison of percentage of enols or stability of enols. Okay, next, if you take another example, see this diketone, it's a tautomeric form, say double bond O, here OH, of course hydrogen bond like that. But if you take this one, of course it is resonance stabilized. if it is drawn tautomerism, see here almost 0%, almost 0%, because of, see this increase in bond angle strain, bond angle strain. Also there is another reason. If you look at its structure, see this, if it is polarized, we get plus here, this becomes anti-aromatic. Of course, mainly due to bond angle strain, we will say this word. So because of anti-aromaticity, here polarization may not take place. That's not the matter. That's why this is the appropriate word here. Okay. Similarly, if you take 1,2 diketones, 1,2 diketones, previously we have taken 1,3 diketones adjacent position. Tautomerism in 1,2 diketones, sorry. With these hydrogens, we have to draw the tautomerism, double bond, OH, here double bond O. Okay, but this is almost 0%. Why? For this ketone, there are two possible conformers. Two possible conformers. This is a syn form. This is anti form. In these two CO groups are in anti position. In these two CO groups are in syn position, like that. If they are always in syn position, we get this one, and it is stabilized by intramolecular hydrogen bond. But it prefers anti position, because in anti position the groups are away and the repulsions are less. So it always exists as in anti form. If they are in anti form, if you look at its enol, is it stabilized by resonance? No. So for the formation of enol here, our percentage of enol is negligible, almost 0%. That's why. In that way we can see different examples. Next, one more factor. If you look at 1,3 diketone steric factor, we are going to see steric factor this diketone can exist in different conformations. See this? See, this is one possible conformation. Another conformation may be like this. Here this is R1, this is R2, this is R3. And another conformation this one. Different conformers are possible, but among those this is better. See, if it is because two CO groups are on the same side, so what? If two CO groups are on the same side, see the advantage. Suppose if it is drawn tautomerism, we get, see, intramolecular hydrogen bond is probable. That's why. So with this is the preferable conformer. Okay. If size of R2, this one, increases, stability of enol decreases because of its conformer. See, steric hindrance See, almost it is a cyclohexane, like cyclohexane system. It hinders the, if its size increases, it hinders the possible probability for the formation of hydrogen bond. Similarly, if R1, R2 and R3, if their size increases, stability of enol decreases. Okay, like that. If these are equal to tertiary butyl, then percentage of enol is 0. So this is the steric factor. Next, effect of solvent. Effect of solvent. See, let's take keto form and its enol form. Keto form and enol form. See, in polar solvents, keto form is stabilized, that is stabilized by resonance. Because of that, the tendency to form enol decreases. That is, percentage of enol is less in polar solvent like water. Okay, but in non-polar or less polar solvents, but less polar, that word is preferable, less polar solvents, percentage of enol increases. Okay, because see here, keto form is stabilized by resonance. Percentage of enol increase relatively when compared to polar condition and non-polar condition. Suppose if the same substance is taken, in polar solvent and less polar solvent. In less polar solvent, percentage of enol of that compound is more. Okay, so this is the effect of solvent. So in this video, what we have seen, different stability of enols. What are the factors? So resonance, we have seen resonance factor, intramolecular hydrogen bond, and steric factor, and effect of solvent. These are the different things we have seen in this video.